Hello there and welcome to A-Level Further Maths. Here we're looking at hyperbolic equations and identities so we can answer questions from exercise 6c. So let's get started then. So method 1 of solving a hyperbolic equation is to just convert it into exponential forms. Let's see that in this question here. The question is 6 sine x minus 2 cos x equals 7. So let's get started then. The first thing we'll do then is we'll turn it into exponential form. So substituting the exponential definitions, sine is this one here, cos is this one here. Let's just tidy it up by simplifying the coefficients at the front and the divisors of 2 inside the definitions. And let's just make sure that when we do the minus, we take away everything inside the cos bracket, so both of the expressions will be negated. Let's now tidy things up a little bit, so simplify your exponentials and then multiply through by e to the x. So you can see what's happened here is that I've got this one here and this one here that's simplified. And that will give us minus 4e to the minus x, but then I've multiplied everything by e to the x at the same time, so that's why the minus 4 is here. The 7 has been subtracted onto the other side and then been multiplied by e to the x, and then the 2e to the x has been multiplied by another e to the x. That's why it's become e to the 2x. So I've done two things here. I've rearranged and simplified, but also multiplied by e to the x on every component. Now what it looks like here is it looks like a quadratic. So I'm now going to factorize this quadratic. 2e to the x plus 1 and then e to the x minus 4 equals 0. So either I've got e to the x equals minus a half, not solvable in real numbers, solvable in imaginary numbers, but we're not going to answer this question in imaginary numbers. So we're just going to ignore the left-hand solution, no real solutions over there. But we do have one on the right-hand side, and that's x equals ln 4. So the answer to this question here is x equals ln 4. So method 1 in solving hyperbolic equations is to convert it into exponential form. Now what I'm going to do next, so this is a proving identities question where I have to prove this identity here, is I'm going to convert it into exponential form. And so the right hand side is equal to this, and I'm going to turn it back into the left hand side. It's always easier to pick the more difficult side and convert it back into the easier side. So I'm starting with the right hand side. Now I'll convert it all into exponentials then. So it's sine 1 turns into this, cos 1 turns into this, plus the cos 1 turning into this, and the sine 1 turning into this. So sorting out the first multiplication, and you'll get half of this big long expression here, and then sorting out the other half, and you get this big long expression here. So multiplying all the exponentials together, you either add or subtract the exponentials with each other. And on the fractions, 2 times 2 will be on the bottom of both the multipliers, so it's 1 over 4 times this big long string of exponentials that have been multiplied together, and therefore the indices add together. Now bits of this do cancel out, and I think we cancel out that, that and that, and we end up with this expression here. We've got 2 lots of e to the a plus b, and 2 lots of minus e to the minus a minus b. Now we can factorize out the 2 and instead write that fraction as a half. And then what we can see is that, are we heading towards what we're actually looking for, sine a plus b? Well, yeah, because we've got a minus sign in between the exponentials, and it's actually minus a plus b on the top of this exponential on the right hand side. So lovely, we've proven that this is equal to the left hand side just by using the hyperbolic definitions. So there we are, we've got an equation that we've solved by turning into exponentials, and an identity that we've proven by turning into exponentials as well. Now the second way that you can solve equations in hyperbolic functions using will not be using the exponential form, but it will be using identities relating to what's called Osborne's rule. Now let me describe what Osborne's rule is. Osborne's rule is that all normal trigonometric identities can be converted into hyperbolic identities. You saw one that was very similar beforehand. You can see that this here is exactly equal to the same trigonometric identity. but there's a slight catch with Osborne's rule. It's not as easy as that. So once again, all normal trigonometric identities can be converted into hyperbolic identities, apart from where you have two sine functions multiplying together, in which case a negative coefficient must be introduced. So whenever you've got two sines multiplying together, use the same identity as you would in normal trigonometric functions, but put a negative symbol in front of it. So let me show you some examples of Osborne's rule. So an example of an identity that will stay the same is this expression here. You can convert this trigonometric identity into a hyperbolic trigonometric identity just by putting h's at the end of all of your trig expressions. The reason you can just do this is because there are no sines that are multiplying together. We've got a sine multiplying by a cosh, which is fine. We've got a cosh multiplying by a sine. That's fine. We haven't got two sines that are multiplying together. But an example of using Osborne's rule where you have to change the identity is with the cos double angle, because you can see at the back here it is two sines that are multiplying together. So when I change this into a hyperbolic trig identity, I'm going to have to introduce a negative coefficient here because I have two sines multiplying together. So this is how this identity would be converted using Osborne's rule. You just put h's at the end of every trig expression, but because you have two sines that are multiplying together here, the coefficients must be multiplied by a -1, so therefore the signs flip over, and they're now, the negative and positive are now upside down. So cosh A plus B will refer to cosh A cosh B plus sine A sine B. So it changes where you have two sines multiplying together. Let's show you a few more examples of this. An example of a trig identity staying the same might be this one here. Cos 2x is identical to 2 cos squared x minus 1. There aren't two sine functions or sine functions multiplying together here, so that the conversion can just be immediate. Just put h's at the end of all your trig functions and you've got yourself a hyperbolic trig identity. But one that will change is the other one for the cos double angle identity, where you've got 1 minus 2 sine squared x. Because you've got two sines multiplying together here, you're going to have to change the sign that's in front of the sine squared. So cosh 2x will be identical to 1 plus 2 sine squared x. So this is an identity in hyperbolics. You can convert this into this one here, but where you see sine multiplying by itself twice, you must change the sign in front of it. If you've ever got sine multiplying by itself 4 times, then you'll have to do a double sign change, which will end up as nothing, or stay the same. I'll show you another one that stays the same in hyperbolic functions. Tan x equals sine x over cos x. That stays the same in hyperbolics. Tan x equals sine x over cos x. But one that does differ is sine squared plus cos squared equals 1, because you can see at the front here you've got two sines that are multiplying together, so the coefficient of that must have a negative introduced in the middle of it. That's why it then turns into cosh squared x minus sine squared x, because the minus had to appear at the front of this sign when you convert it into hyperbolics. Another one that changes is, it's a little bit of a tricky one, this one, is tan 2x, so tan a plus b, that's supposed to be tan a plus b there, tan a plus b is equal to tan a plus or minus tan b, all divided by 1 minus or plus tan a tan b. And you're probably thinking to yourself, where have we got two sines multiplying together? Well, it's inside this tan a and tan b, because you're going to have sine a over cos a multiplying by sine b over cos b, and inside that multiply of tan you have two sines that are multiplying together. So what will happen here is the top will stay the same because you haven't got two sines multiplying there, but this bottom will change. You see the change in the minus plus to the plus minus. Tanh A plus B is equal to tanh A plus or minus tanh B over 1 plus or minus tanh A tanh B. So there we are. So that's a kind of a hidden place in which Osborne's rule must still be applied. We've got a couple more maybe. This one will change. So tan squared x plus 1 equals sec squared x. So we've got two sines multiplying together inside this tan as well. So it's going to be minus tanh squared x plus 1 equals sec squared. And the same thing will happen here, but you've got two sines multiplying together inside the cot and inside the cosec, because that's 1 over sine. So in fact here it turns, both of these things are going to change because they both have a sine, two sines multiplying inside them. So we have the new identity, which is this one here. Why? Why does Osborne's rule work? Well, you'll understand this more if you've watched the previous video, which was Hyperbolics just for fun. We've got 4 rules that link the hyperbolics and the normal trig functions at the top of the screen there. So how can we show that Osborne's rule works? Well, any identity with cos A, cos B in it will be fine. And if we set A equal to IA and B equal to IB, we can see that that will stay the same when you do it in hyperbolics. So what I'm going to use is I'm going to use this third identity at the top here. So I'm now going to convert my cos IA times cos IB into cosh AB. Use the identities from above, and you've just got cosh A times cosh B. So any time that you've got two causes that multiply together, then just replace the A and the B with IA and IB, and that will just turn it into an expression in terms of coshes. So there's no sign change involved there. But when we do the same with sine A and sine B, if I replace A with IA and B with IB, then this is what I'll get. And it's this identity that I'll have to use here. But notice that this identity is different to this identity here. The third one is different to the fourth one because there's an I at the front of the shine. So for sine IA, I'm going to have to turn it into I shine A. And for the sine IB, I'm going to have to turn it into I shine B. So using that identity from above there, I've got I shine A times I shine B. And then simplifying this now, I'll get the two i's and multiply them together. So that'll be I squared shine A shine B. And then that I squared will turn into a negative. So that is exactly why Osborne's rule works. It's because the link between normal trigonometry and hyperbolic trigonometry is defined by these 4 rules above. And when you substitute a imaginary number into a cos, nothing really much significant happens, but when you substitute an imaginary number into a sine, an imaginary component I appears at the front of a sine function, and then the two of them combined will multiply together to make yourself a negative there. So that's why Osborne's rule works. So let's now see some questions in action where we can use Osborne's rule. Let's answer this question here. 2 cosh squared x minus 5 sine x equals 5. Okay, well usually if I was answering this question in normal trigonometry, I'd want to turn the squared function into the linear function so that I've got then a quadratic, and I can then solve that quadratic by brackets or by quadratic formula. So I'm going to recall the rule that cos squared x plus sine squared x equals 1, and then apply Osborne's rule to it. The two sines multiplying together will make the plus sine squared x into a minus sine squared x. So I'm now going to rearrange this a little bit. Add the sine squared x onto the other side, and I get 2 brackets, 1 plus sine squared x minus 5 sine x equals 5. Open up the brackets, and now we're on our way to solving a quadratic. So we've turned the cosh squared into a sine squared by this identity here. This is an identity that stems from Osborne's rule. So we've got this quadratic expression here. Let's now factorize. So I've got either sine x equals minus a half or sine x equals 3. And recalling the our sine formula, which is ln x plus root x squared plus 1, I've got two answers here. I've got this turns into this thing here, and sine x equals 3 turns into this expression here. So that's an example of where I can use Osborne's rule to solve an equation. Let's have a go at another one then. This one here is cosh 2x minus 5 cosh x plus 4 equals 0. So what I'm first going to remember is that there is a rule in normal trigonometry that follows this. Cos 2x is identical to 2 cos squared x minus 1. And I'm going to convert this rule into a hyperbolic identity using Osborne's rule. And Osborne's rule is not going to change this formula at all, because Osborne's rule does not have, so this identity here does not have two sines multiplying together, so I can just put h's at the end of the trigonometric expressions. So cosh 2x is equal to 2 cosh squared x minus 1, so I'll replace this with this here, what it's equivalent to. Let's now simplify, and now some brackets, and then solve those brackets. Cosh x equals 3 over 2 or cosh x equals 1. Use the identity of r cosh, and we're going to get ln 3 over 2 plus root 5 over 2 and 0. So there we are. Now, I would never prove an identity using Osborne's rule. Osborne's rule is a friendly way to remember the trick between normal trigonometry and hyperbolic trigonometry. If you're proving an identity in hyperbolics, it's got to be done using method 1. But you can solve equations by using the identities that relate to Osborne's rule. Now, just to finish off this question here, just a reminder that when you solve any cosh inverse functions, because the graph is symmetric, you've got to include the plus or minus of that answer, because any answer like ln 3 over 2 plus root 5 over 2, if that is equal to 3 over 2 on the cosh graph, then so will the negative version of it. So you've got to remember that for cosh equations, make sure you do a plus or minus at the end of your answers. Okay, so let's have a go at a question here. Pause the video and give this one a go. Okay, so this is a standard question that we need to be able to solve, leaving our answers in exact form. So I see here I've got a sine squared and a cosh in this equation. So what I'll remember then is that I can convert, I've got the identity, what is it, sine squared x plus cos squared x equals 1. I remember that from A-level maths. But when I introduce hyperbolics, I've got two sines that are multiplying together here. So it's going to be cosh squared x minus sine squared x equals 1. So if I want to get rid of my sine squared, I'm going to have to move it onto the other side and take away the 1 onto the left-hand side, just like that. So this equation now turns into 2 brackets cosh squared x minus 1 minus 5 cosh x equals 5. So let's now expand the brackets. It's going to be 2 cosh squared x. I'll get a minus 2, so that when I move the 5 over, it's going to be minus 2 and minus 5, so it'd be minus 7. So minus 5 cosh x minus 7 equals 0. I can probably put this into some brackets. 2 cosh x and cosh x. Now it'd probably be the plus 1 on this side and the minus 7 on this side to make it minus 7 cosh, and then add 2 cosh there. That would be fine. So either we get cosh x equals minus 1, and you've seen the graph on the previous slide. The graph of the cosh function looks like that, so it's never equal to minus 1, so there's going to be no answers there. But cosh x could equal 7 over 2, or 3.5. So let's now work out what this is going to be. It's going to be x equals plus or minus, because the cosh equation will always give you a plus or minus answer. Then it's going to be ln, and then it's going to be 7 over 2 plus the square root of, and let's use the identity, it's going to be 7 over 2 squared, so 49 over 4 minus 1. So x equals plus or minus ln 7 over 2 plus, that would be 4, so it would be 45 over 4. 45, is that a third? Could we simplify 45? Yes, 9 times 5, so that would be 3 root 5. So I would say this could simplify into 3 root 5 over 2. And there we are, that's the answer. That's the two answers for this equation. It's a plus or minus at the front of the ln there, because the cosh graph is symmetric. Any positive answers will also be the same on the negative side as well. So there we are, that's all we're going to go through in this video here. Make sure you have a go at lots of questions from page 128, exercise 6C. Make sure you have a go at the problem solving ones, the exam style questions. And I just want to finish this video off by really highlighting the point that it's not acceptable to prove identities just by saying from Osborne's rule. If you want to prove an identity, you have to do it through exponentials. But if you want to use cheeky Osborne's rule to solve an equation in hyperbolics, then that is acceptable. If you want to use Osborne's rule within the context of a question, that's fine, but Osborne's rule is not good enough for when you're trying to prove a hyperbolic identity. Lovely, hopefully that's clear, and thanks very much for watching.